And so our next speaker is Gunther Just from Manchester. Please go ahead.
With you in person today. That's why I pre-recorded my presentation, in which I will show you what we developed over the last couple of months. And this is the Lunar excavation size separation system for the LUVMI-X Rover platform, or in short, less cubed. And it's a project that we've been running at the University of Manchester with the UK-based Space Hub and also our industrial partner, Space Applications Services, who built the LUVMI-X Rover. All right. So if we're looking at the ISRU process chain, you can see that it all starts with the excavation of the feedstock, in this case, the regolith, which then most likely has to be beneficiated. Beneficiation in this regards is a mining term, which means basically improving the quality of the feedstock before this improved feedstock can then be processed by any ISRU processes. So your 3D printings, your oxygen extractions, and so on. But as we can see often right now, excavation and beneficiation are investigated as completely separate process steps with a handling process in between. So this might be your excavator excavates, is then hauled to a beneficiation site, and from there you go on. But what we thought was really interesting is how, or looking into how can we combine excavation and beneficiation into only one process. So this seems beneficial to the whole process chain and its robustness, because we eliminate this intermittent handling step. And if we think about different ISRU processes, they all have different requirements. So if you think, for example, additive manufacturing, so for example, selective laser melting has very different particle size requirements than, for example, large-scale construction. Or oxygen extraction application, for example. Some might have no particle size distribution requirements at all, others may do. So basically what you can see is different regolith end users, we call them, require different levels of size separation. But if you look at all the available literature that detail those processes, you can often see that the lab tests only use a certain size fraction. So you read sentences like we use the SIF size fractions below 125 microns or something like this. But usually that's about it. So there's no details as to how you would obtain this size fraction on the lunar surface, or if it would even be possible, which is, in my opinion, really important to know, because if your particle size distribution requirements are too extreme, let's say, it might not even be feasible on the lunar surface. So that's the kind of idea behind the mechanism I'm about to present. Just a couple words about what was the aim of the whole project. So on the left, you can see a rendering of the LUVMI-X Rover platform. So LUVMI stands for Lunar Volatiles Mobile Instrumentation. X is the second rover in this family. It's a small, lightweight rover, about 40 to 60 kilograms, and low mass on the lunar surface means we only have a limited amount of traction, which then in turn also means that we can only use limited excavation forces to actually get the regolith out of the ground before we get stuck. So the aim was to develop a low mass, low excavation force mechanism, which is capable of not only excavating the regolith, but also size separating it, which then becomes one of the three main functions it has in support of ISRU, but also science. So as you can see in A, we want to excavate and beneficiate the feedstock into two different size fractions that we can then deliver to different ISRU processes. Secondly, the rover has a LIPS system mounted on its beam, and we can support this by uncovering different layers of soil, for example. And then the third point here is that by digging trenches, for example, we can enable the investigation of geotechnical properties of regolith. So the mechanical design that we went with, so here on the left, you can see a sliced pad view. The system, or the mechanism, consists of three distinct parts. So we've got the base, which is basically a turret, which allows us to rotate the the whole mechanism, which is mainly used to store it in Rover during launch. Then we've got an arm, which you can see here in the middle, which is divided in the middle, so along its long axis, into two compartments, which is basically two slides. And on the top you can see a chute, which is for the coarse fraction that we separate, and then the bottom one will be for the fine fraction. And then they come out at the end, two size fractions, which we then collect. And then there's the inlet. The inlet is the most important part because it actually is the part that excavates, but also performs the size separation. So as you can see, we've got two screens here. We've got a coarse front screen, which is basically the first step of size separation in our two-stage process, and then we've got a finer screen, which is the second step. So that's how we get our two distinct size fractions, and those size fractions are then ejected after separation through spring-loaded gates, which are actuated by a cam follower system to keep the system as passive as possible. So you can see we will have a coarse fraction sitting on top of this screen, which will then be ejected through this this gate basically here, which is actuated by this profile. And then our fine fraction will be here coming out through this gate, which is actually actuated by this profile, but I'll explain it in a second. And yeah, then the two size fractions are transported within the arm, as I said, to the storage containers. So we can activate and transport to a storage location in one go. And we are using vibration to reduce excavation forces while actually digging, but then also for size separation and for transporting the materials down the chute. So basically like a vibrational conveyor on Earth. A bit more detail. So here you can see the mechanism in action in our analog testbed that we have at the University of Manchester. So yeah, here you can see the inlet and the front screen. In this case, this is a 2mm frontal screen. You can see the springs here closing this gate when it's not in operation. This is the vibration motor that we use for the experiments, the other cam profiles, and the chute. Here another view from the side. So here's a nice view. You can see the gate is closed. The follower sits in its idle position, and therefore everything's closed. We can acquire the material, and in a second I'll show you how the whole process evolves. And just on the right here, some more details of the cam follower system that we use. So this is the gate for the fine size fraction. So here you can see it's closed, as I said, but then when it's actuated, it looks like this. So the gate is fully open, allows us to eject the fine fraction of the reglet. And then on the right here, you can see the gate for the coarse fraction. Again, here closed, and then here fully engaged, which means the sliding gate is open in a position where the portal to eject the material actually mates with the chute, so we don't lose any material. So the operating principle, just a brief overview. It is basically a 4 to 5 step process, which you can see here as actual real life pictures and a schematic at the bottom. So first, we lower our arm and bring the inlet into a position of a shallow cutting angle or digging angle. Nowadays it was around 15 degrees because we found this is a good angle for low excavation forces. And then the whole mechanism is pushed forwards by, so you can see here, pushed forwards by the rover. And then once we acquired enough material, we move into the pre-separation phase, which is phase 2 here. So you can see the arm raises itself to a certain level, the inlet even further. In this position, the gates are still all closed, all material stays within the inlet. We then activate the vibration motor, which means any material that we excavated in front here is pre-separated through the first screen and falls into the second chamber. We then, when this is completed, we move into position 3, in which you can see the arm raises itself a bit more. The inlet comes down, which means the cam follower system is actually engaged, and the profile is calculated in a way that it opens slowly first, and then it basically increases the opening rate towards the end. So when we get closer to the two parts actually meeting each other, so we can eject the material without losing too much material. Then once they so the outlet port and the inlet in the arm are connected, we then activate the vibrate motor again to perform the size separation, the second step of size separation, and all the fines basically fall through the arm into the storage container. And once this is completed, so in the storage container, it's intended to have a load cell measuring the acquired material. And once there's no change observed anymore, we say the separation is completed, and we move into position 4, which is then the ejection of the coarse fraction. As you can see, as I have explained, this cam follow system engages, and then we eject the coarse fraction. And then afterwards, number 5 is a cleaning step, which I will not detail too much here because of time. But yeah, this is the basic operating principle. And then we tested this, of course, in our test bed. So just some performance facts and some future work at the end. The mass of the whole mechanism, so including the base and everything, is below 2 kilograms, and we can excavate up to 100 grams per scoop. This was at a 3 centimeter cutting depth, so the mechanism really focuses on the top 2 readily powdered centimeters of the regolith. And we were able to do this with excavation forces, terrestrial, of course, below 8 newtons, so, which is really good given the fact that small rovers only have a certain amount of traction available, and we were able to successfully test size separation down to 500 microns in the fine with the fine sieve, basically. To inform the aperture size that makes sense and how long the whole size separation would take, and also just investigating gravitational dry sieving of regolith more, because it is often considered very difficult to do, of course. We set up a standalone experiment doing this and tried this with several simulants. I haven't included details of this experiment in this presentation because it would have been too long, but if anyone is interested in the results, please feel free to contact me and we can have a chat about it. And then just lastly, the future versions of this mechanism, what is left to do? It needs a lot of dust proofing, of course. There will be of the final materials and sensor selection. We want to further reduce the mass and also the dead volume so that we don't acquire regolith in areas where we can't get rid of it anymore. And then lastly, later this year, we're looking at a field test with the actual Rover breadboard in Belgium. And yeah, so thank you very much for your attention. And if there's any questions, if you're interested in anything, please feel free to get in touch. My email address is up on the screen right now. And there's also some videos of the mechanism in action that are public. I posted the links in this presentation, so feel free to check it out. And if there's any questions, get in touch with me. And yeah, thank you very much and enjoy the rest of the conference.